Okay, today is week 2 of the lectures, and we're going to talk about linear momentum. Linear momentum is something that we have gone over in basic science class, so some of these concepts you've already seen before, but we're adding some further definitions which increase somewhat the complexity of the concepts. Linear momentum is the product of the mass of an object times the velocity of the same object. So P, which is a letter that's frequently used to delineate linear momentum, time is equal to the mass times the velocity m times v. Momentum is a vector quantity, and that is very important to remember. Therefore, it has both a size or a quantity or a magnitude and a direction. The force that's applied to any object is equal to the change of the momentum in that object over the change in time. This is a reiteration of the second law of motion. So that makes F net times t a quantity known as impulse. And impulse is equal to the momentum. Now, just as energy is conserved in any system, momentum is also conserved. So in this diagram, you have a car with a mass m1 moving at velocity v1, which is faster than the car in front of it, mass m2 and v2, and it bumps that first car, the second car that it's following. As a result, the first car slows down to a new velocity v1 prime. The second car speeds up to a new velocity v2 prime. The momentum of each car has changed, but the total momentum within the system of interest of the two cars is the same before the collision and after the collision. And obviously this assumes that there is no friction between the two cars. Here's another situation where you have two objects, a single rocket that is flying, and the horizontal component of this projectile is conserved if the air resistance is negligible, even though the rocket separates into two pieces. The forces causing the separation are internal to the system, so that net horizontal force is equal to Fx minus F net, and that is still equal to 0. The vertical component of the momentum is not conserved because the net vertical force, Fy minus net, is not 0. In the vertical direction, the space probe, Earth system, needs to be considered, and we find the total momentum is conserved. So the center of mass of the space probe takes the same path it would if separation did not occur. And so what you see here is that what looks like a loss of conservation is due to the way in which the system is reviewed. This is also in your book, and if you're having trouble understanding that, just take a look at the explanation in the book as well. Now, there's two kinds of collisions that we have to talk about, and the first one is called an elastic collision. An elastic collision is in a one-dimensional situation is where the momentum and the internal kinetic energy, that is the kinetic energy within the system of interest, is conserved. So both the momentum and the internal kinetic energy is conserved. So for example, in this situation, we have before you have two masses sliding, and the total momentum is equal to this. There is no force exerted. There would be, if these are both moving, these two would have kinetic energy, represented down here as K1 and K2, KE1 and KE2. And then after the collision, you'd have another momentum, and this total here and this total here have to be the same. And these two kinetic energies after and these two kinetic energies before also have to be the same for this to be an elastic collision. So let's take a look at a couple of problems taking into account conservation of momentum and elastic collision. And the first problem is primarily a problem to look at conservation of momentum. And what we have is a 900 kilogram car that's traveling at 30 meters per second. And it hits a deer 150 kilograms that's running at 12 meters per second, and both are moving in the same direction. And the question is, if the deer remains attached to the car, what is the velocity of both the deer and the car after the collision? So let's take a look at this problem. And so we have a 900 kilogram car, and that's the mass of the car, so we'll call that M1, and the mass of the deer is 150 kilograms, and the velocity of the car before the collision is 30 meters per second. And the velocity of the deer before the collision is at 12 meters per second. Now, the two stick together after the collision, so the mass of after the collision is going to be the sum of the two, or 1050 kilograms. And so what you have is M1V1 plus M2V2. That is the total momentum of both the deer and the car before the collision has to equal M1 plus 2 times V3. We'll say V3 is the new velocity. If you put all these numbers in, you have 900 times 30 plus 150 times 12. They're moving in the same direction, so you'd add them together, is equal to 1050 V3. And so if you solve for V3, you get 27.4 meters per second. Now, does that make sense? Well, yes, it does, because if a faster moving object runs into a slower moving object, then the faster object is going to slow down. And since they stuck together, both of them, and the slower object is going to speed up, well, the deer speeds up and the car slows down. So the answer does make sense. Now let's take a look at the second problem here. The second problem says you have a recoil, 70 kilogram, find the recoil velocity of a 70 kilogram goalie who's originally at rest, so he's not moving, after he blocks a 0.15 kilogram hockey puck slapped at him at a velocity of 35 meters per second. And it's an elastic collision. Find the velocity of the puck in the opposite direction. Okay. Now this one is a lot more complicated in terms of the mathematics here, because what you have is an elastic collision. So first of all, the momentum in the beginning before the collision has to equal the momentum after. We'll call this before and after. And the momentum before, first of all, let's assign the goalie is at 70 kilograms, and he is not moving, so that's 0. The hockey puck is 0.15 kilograms, and it's moving at 35 meters per second. Now afterwards, the hockey puck is moving at a new velocity, and so is the goalie. These are two unknowns. Okay? The goalie is moving in one direction and the puck's recoiling in another direction. Now, how do you get this? Well, the second equation is that the kinetic energy has to be conserved. So 1/2 m1 v1 squared plus 1/2 m2 v2 squared has to equal 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. Okay, so now you have that equation plus the original, which is that the momentum of the hockey puck, and you don't have to worry about the momentum of the guy because he ain't moving, has to equal the momentum of the guy after the collision plus the momentum of the hockey puck after collision. So you have two equations and two unknowns. And so V1 is 0, so we can get rid of this, and I already got rid of the first one, this M1 V1, so we got rid of that too. So you can put numbers in and you end up with two equations and two unknowns. So you have 1/2 times 0.15 times 35 equals 1/2. I'm sorry, there's no 1/2 here. Get rid of that. Is equal to, it's this, I'm writing this one down. Is equal to 70 times V1 prime plus 0.15 times V2 prime. Okay. And then 1/2 times 0.15 times 35 squared has to equal 1/2 times 70 times V1 prime squared plus 1/2 times 0.15 times V2 prime squared. Now you can see we have two equations and two unknowns, and I'm actually not going to go through the process here. It's actually quite long and drawn out. What I did was to take this and solve it for one of these two and then substitute it in this one. So if you take this one and solve it, this is 5.25 is equal to 70 V1 prime plus 0.15 V2 prime, so that V2 prime equals 5.25 minus 70 V1 prime over 0.15, and you can take that and put it right there and then solve this one, and that's a little bit more complicated. If you do all that, I got for V2 prime 34.85 meters per second. It's actually in the opposite direction, and that makes V1 prime 0.15 meters per second, which makes sense. A big goalie gets hit by this, it's going to be a pretty small number. So that makes sense for the goalie, and then this is bounced off at about the same speed in the opposite direction. But you can go through that if you want to and check it out. Before we move on, well actually we are going to move on. When I return for the next lecture, we will start talking about what's known as an inelastic collision.